spatial epidemiology, geographies of health, public health, geographic information systems, and remote sensing. So those of you who are also interested in application of spatial intelligence to health, you can as well get in touch after the webinar. All right. So why are we doing this? We expect these are some of our expected outcomes. So at the end of the first webinar series, we expect all of us to be aware of the background, like the context under which meta-analysis was actually made, the essence or the importance of it, to know the difference, critical difference between the meta-analysis and systematic reviews, some key features of meta-analysis, and then the difference between fixed and random effect meta-analysis, very critical. And then I will also be made available some software lists that we can use, whether they are free or not. Oh my God, please can everybody, if you're on mute, can you please mute yourself so you don't.
But can you please go on slideshow so that we see the whole screen better? Thank you.
You may kindly also start again. Thank you.
Hello, Dean.
We cannot hear you. You are on mute. We cannot hear you.
Hello, Dean. Can anyone hear? Yes.
Yes, I can hear you.
Looks like I was muted, so I am kind of slideshow. All right.
Can you use slideshow at the end of the slide in the bottom?
Can you? Is it showing in the slideshow format now?
Yes.
Perfect.
Yes.
Okay. Very good. So from this is Community for Systematic Reviews and Meta-Analysis, ACSRM, which is like an African-based community for improving evidence-based methods in health, primarily. So if you want to know more about this community, you can visit the link that I have put forward here. All right, I've already introduced myself, so we go straight to the outcomes. So background of a meta-analysis, the essence of it, to know the difference between a systematic review and meta-analysis, some key features, the differences in the models that are used for this process, and then some key software available. So technically, just to give a brief overview of this approach. So before meta-analysis, there were traditional or narrative reviews that were done by experts in the field. So if they needed to make an overview of a particular area, especially in some of the clinical fields where you need to be able to know if an intervention is working or not, these were handled primarily by narrative reviews. Since they were not having scientific rules, they were done by experts in the field. And the scope, definition, the procedure, and the conclusion that were drawn were arbitrary, and it was going to be decided by the one who was doing it. Of course, that was providing some level of help, but it was more biased towards whoever was doing it. And so they needed to move to a much more systematic approach in doing it. Like that should follow some form of like a conventionalized rules in setting the method, the questions to begin with, the methods in selecting your studies, how to synthesize your studies, and how to validate the studies. All of these were kind of conventionalized approaches, but pretty much more, it was still more narrative in a way, but it was better than the traditional narrative reviews. Then came the meta-analysis as a concept. It has existed for some time, but it was later on that in the 80s that it became publicly available. But then just a quick overview of it, we all probably may have heard of a Pearson R-squared and some other forms of things like Pearson, Carl Pearson, and then Ronald A. Fisher. These were prominent statisticians of their time, and they still are today because most of their methods, we still rely on them today for our statistical analysis. These were the first two people who started applying the concept that we know today as meta-analysis. Pearson really applied it in knowing the prevalence of typhoid inoculation in the British Empire during the time where typhoid was a major problem. And so they needed to know if somebody was vaccinated or got some form of interventions, what were the prevalence or the portion of the population that were actually under this intervention. It was carried forward by Carl Pearson. And then Fisher Ronald was also one of the first to have also applied this same idea in agricultural analysis as well. However, this was still not known as meta-analysis until there was an issue with clinical psychology. I'm sure some of you may be coming from psychological backgrounds, but there is a brief story about Sigmund Freud, who introduced some models to have like the way we can improve patient outcomes in terms of psychotherapies. This was more like a gold standard in psychotherapies and clinical psychology until the 1950s or the 1970s, where a particular psychologist by name Hans Jegen, this guy published a paper who the outcome or the conclusion was that the Freud approach in approaching psychotherapy was not efficient. And in fact, if there was any outcome at all for any patient, it was because the patient was actually doing fine, not because of the approaches that were being used. And to be known, this was like a major big blow to the field. And his publication influenced the whole clinical psychology and psychotherapy for nearly 2 decades, until the 1970s, where there were people who took forward this by name Genevieve Glass, who was considered as the founding father of meta-analysis in Italy. He coined the term meta-analysis, and he applied the approach in actually analyzing psychoanalysis effectiveness in the 1950s. Who is talking? Please, if you have a question, you can put it on the chat box. All right, thank you. So he applied this concept and then later on gave us the meta-analysis. And the conclusion he came out with, he did mean differences, which was not really standardized, but at least it only concluded that there were the mean differences of 0.68 was large enough. So the end of it was whatever Jegen Han said about psychotherapy or Field's approach was wrong. So he held the psychology hostage for 2 decades, which was later proven that his claim or his verdict was wrong. And of course, that would not have gone well with Jegen because he was still alive then. Oh my God. Coming. So it was later, if you can see a quick debate box I have indicated here, he replied with a quick blow. He said that was an abandonment of scholarship and an exercise of mega silliness. I have actually included this paper as part of the references. You may want to know more about this debate, you can read it. But it didn't really stop scientists from building on this approach because he was wrong. Of course, the 0.68 was much more inflated because at that time, the method wasn't strong enough. But still, later on, most studies that use the same approach prove that Elizabeth, can you, if you have a question, you can raise your hand and then I can call you. Okay.
The co-host should please take care of all this.
Yeah. Fortune. I don't know if Fortune is available, but Rosine.
Please, I am doing that. Please,
Okay.
it's okay. Thank you. You can continue.
All right. So we could see that judging was wrong. And so later on in the 1970s, all right, Simon, you have a question? Simon, have seen your hands raised?
Please, we are going to take questions at the end of the season, please. Thank you.
All right. Then, so that was the brief introduction of how the whole thing started. But of course, I should acknowledge that beside Genevieve, there were other people who also Genevieve Glass, sorry. There were others who also contributed to this meta-analysis. One of them include Cochrane, and who is currently we know as Cochrane Libraries, and we go on to kind of get some of our papers and read more about synthesis and startup. Yes, Cochrane was really one of the few people who also contributed immensely to the discipline. And then Peter Elwood, in fact, that was a colleague to Cochrane. So both of them worked together on aspirin form of effectiveness with a meta-analysis approach. And currently we do have Cochrane and Campbell collaboration and all that, which are more, is really important. And now we can move on to some form of why is it needed? So far, I think the brief background would have already said more about why we need it. But formally, I have from the literature, I think I'm able to get 5 main critical reasons why we need them. One of them includes increased statistical power. Normally, the individual studies may include samples like 200, 300. So imagine the whole of Nigeria, 200 million, and you are nearly 200 million, or probably above that. And you sample 300, and you want to make generalization with that 300 sample size to over 200 million people. It doesn't work. And of course, even if it ends up, it's not really reliable. And so when we get a meta-analysis to pool studies from a broad population, which may increase our sample size to probably 1 million or 2 million, it helps to increase the confidence that we have in anything that we are doing. Secondly, it enhances the generalizability, how much we can generalize. Of course, that relates to the first thing I made. If you have an increased statistical power, then anything that you are making, the conclusion drawn, is always can be made generalizable to the entire population, which is very, very important. And of course, also resolution of conflict in findings. So let's assume there is an issue with this COVID vaccines. Others are finding maybe J&J is effective. Others are saying it's not effective. So you may come out from multiple research dimensions. Some of them may find negative effect of it. Others may find positive effect of it. How then do we resolve this conflict in the ongoing scientific evidence that we are building for the particular vaccine? Then meta-analysis becomes handy. We pull all these conflicting studies together. Generally, we now can come to a summarized evidence. Is the drug effective, or is the vaccine effective or not? Then we can resolve the conflict that would have been ongoing. Then we have an increased precision and accuracy, much more related to the statistical power. When you have more statistical power, then less standard errors and then higher accuracy. And we can also identify where, if really we are examining effectiveness of a vaccine, of course, maybe different population groups may have different outcome to it. Then we do this meta-analysis, we quantify the overall variance. There is significant variances, regardless of whatever we are considering it. Then we can explore why is there variances across. Then we can come to a very critical conclusion that, the drug works for this population, let's say Ghanaians, but it doesn't work for Nigerians, or it doesn't work for Ethiopians, primarily because of these A, B, C, D reasons. These are some of the critical reasons why we need them. And so we move on to, of course, these were some golden optimistic reasons why we need them, but it doesn't mean it doesn't fall short to some of the things I'm going to be mentioning here as well. Some of these pitfalls that I have acknowledged here can be handled with care. So I'll go with one by one to each of them. One of them includes something we call the apple oranges. So provided you want to pool the effect of a vaccine on, let's say, COVID-19, and you are dealing with different vaccines that are developed by different companies. Oh my God. So we are dealing with vaccines that are being produced by multiple companies. Then we do meta-analysis combining all these together like as if they are just one single thing. Of course, they are dealing with that single diseases, but probably the methods in developing them, some of them may be, hello, Rosalind, can you make sure you handle this? All right, thank you. So we have this approach and we cannot basically throw out all these vaccines together like as if they are the same thing. They are, of course, targeting COVID-19, but some of them may be RNA-based, others may not be RNA-based and stuff like that. So we need to be very, very careful about how, because we can pool doesn't mean we should go ahead and start doing it. We need to be very critical that we are not really combining orange and apple together and then saying we are pooling evidence, because at the end of the day, it's going to be very misleading and then utterly useless to anybody who is going to use it. It's another thing also about garbage in, garbage out. Why we are also conducting this kind of webinar series. Quality matters. So if you are including poor studies and pooling, the overall effect of your meta-analysis only going to magnify the errors. It doesn't decrease them, because why meta-analysis? The first one is to increase statistical power. Of course, you may be increasing statistical power in a wrong way. Why is that an issue? It is an issue, provided you have just aggregated all flawed studies. You are only perpetuating lies, and in fact, you're making the lie much more bigger. And that is going to be very, very detrimental to anybody at all that's going to use. And mind you, meta-analysis is like at the apex of all evidence pyramid, not even individual-based clinical control trials. So you can be very careful about garbage in, garbage out kind of analysis. And then currently being, because of Cochrane and Campbell collaborations and other forms of organizations, we now have risk of bias tool assessment and quality assessment tools that we can rely on to, weed out all the, non-essential or potentially flawed studies. So we can focus on more critical ones. And there is also an example of a file drawer problem. There's also a likelihood that because normally when we are doing this meta-analysis, in our inclusion criteria, almost all studies will come across this like, okay, I'm using only published studies. I'm using published studies. How about the non-published ones, like dissertations and stuff like that? Some argue that some of these studies should be included because they may also be having some views that are not shared by the published studies. And of course, because the study is published doesn't mean it is 100% accurate. So we need to be very careful in a file drawer problem. They suggest that you can go beyond this, include dissertations and some forms of primary studies, including preprints and stuff like that, should be included broadly so that we can do, at the end of the day, do some form of like sensitivity analysis to know all these, because at the end of the day, publication biases, you may only rely on the published studies, and then it might give you some effect that, okay, the vaccine is effective. Maybe there's like some dissertations elsewhere that are not published yet, but that is having an opposite view of that. How about that? At the end of the day, your studies may be potentially misleading. So that is why we need to be very careful about the file drawer problem as well. And then the researcher agenda. This is very difficult to handle because there isn't any statistical way of really telling somebody what you call it, the agenda behind why you're doing this. Maybe I am a company, like maybe Big Pharma. I'm trying to see how effective my drug is. So I've employed some scientists. It's influencing them how, okay, I want the scientists to prevent the evidence that the drug I'm developing or I've developed is effective over the 10 years period. So because they have the agenda of making sure that the company having a good name or the drug keeps selling, then they can potentially only select studies that are reporting positive outcomes. And that can be also be detrimental to science. And that is why you, the researcher, has to be truthful at the end of the day. And you also have to be unbiased and objective. And of course, it's very important. That's why it's a systematic analysis or systematic approach. When you lie, somebody can also take your same approach and redo it again and see if they will arrive at the same conclusion or not. And that is the beauty of science. Your studies can always be replicated or reproduced to see whether the conclusion you have arrived is reliable or not. And I think these are some of the pitfalls that I have acknowledged. We can all see that they can be handled one way or the other. So because of the pitfall doesn't mean you shouldn't go ahead with it. You should be trained critically in it, and so that you can acknowledge, you can identify all this problem I've identified, and then how to address them systematically. And then I move on to the effect sizes. These are very, what do you call it? Very important as well. So in a meta-analysis, it's common that when you're reading the literature, you would see something like effect sizes. People from medicine, you might see like treatment effect. Okay, I have developed a vaccine or I've developed a drug, and then I've given to people. I developed, let's say, I did randomized control trials, control group, treatment group. I assigned each of them the drug, and at the end of the day, I measure what is the mean differences in the outcome. For example, if I was going to assess, for example, the number of cell pool in each of them. At the end of the day, was the drug in A decrease the cell pool versus B, then I can get the differences, and that may become my treatment effect or something of that sort. So we have different treatment effect sizes when we come to meta-analysis. The term itself is a little bit problematic, I think, because not everything is of effect, and not everything can really be, not every effect is a treatment effect, of course, because we have a relationship between income and then some form of mental health. This is not like, medically, treated stuff, but technically, income do have an impact on whether the person may do well or not do well mentally. And so we need to be very careful when we are using the term effect sizes. It doesn't simply mean only treatment effect. And of course, in the meta-analysis, you may also come across people reporting prevalence of diseases or prevalence of certain forms of cancers and stuff like that. Itself is not a treatment effect. It's only giving us like a proportion of the population that is having the diseases. But then generally, we can refer to all of these as part of effect sizes. And that is what we all use in our studies. And then why does it matter? It matters because you, the researcher, has to understand which effect sizes we are doing. If you are trying to see the impact of, let's say, air pollution on cancer, you have to be knowing, am I going for correlation studies? Am I going for studies that are more of like binary outcomes, like yes or no kind of studies? Am I going for, so you have to be very, very careful about the studies that you are pulling and then the metrics under which you are measuring them. And here I identify that your effect sizes should be comparable across studies. We should be able to compare them. For example, the impact of COVID-19 on mental health, they should have like a common metrics under which they are measuring the impact. You cannot just be pulling different effect sizes to get different types together and then jungle up together and say you are doing meta-analysis. It's wrong. And so they should too be computationally feasible. Why do I mean feasible? Not every single thing can be actually pulled in a meta-analysis. So you should know. Okay, so also it should also be reliable. We should be able to rely on whatever you're interpreting. In clinical sector, in other non-clinical sectors even as well, we have trusted effect sizes like correlation, relative risk, odd ratios, and stuff like that. That we can all know that these are reliable metrics of effect sizes. So yes, and of course, it should also be interpretable. We should be able to interpret them. That a relationship between X and Y is 0.6. That is easy to interpret. Yeah. Then we go on to doing some form of, imagine in the meta-analysis domain, you can always see like these effect sizes are normally represented as theta. Theta is normally the summarized version of all the studies. So if you have identified 70 studies of the impact of COVID-19 on mental health, it's likely that you want to look at it broadly in the whole continent of Africa. What was the overall impact of it? We can identify that, okay, if we should have included every single African, which is currently about 1.2 billion people, what is the effect of COVID-19 on mental health? Then whatever thing we've come out with will represent our theta, which is our true effect size of the overall population. However, instead of individual people being our unit of analysis, we are rather using the studies as our unit of analysis. So in this case, we are trying to say that each study was conducted correctly, and every single population that they assessed, like people that conducted the studies from Nigeria, would have used all the people from Nigeria to conduct the studies, like 200 million people. So we are saying that the effect sizes for study K is true for Nigeria, so that it can be generalized to the rest of Africa. But then that is not also entirely true, because we can never sample the whole of people in Nigeria. We're always going to pick a sample like 200 people, 300, or probably 10,000 people, and it's still not the whole of Nigerian population. So we are always going to deviate from the true effect size at the end of the day. So how do we deviate? We have some error. Every sampling techniques will always give us some error. So when we add the error to what would have expected in the study, then that should give us the true effect sizes. Or in other words, I'm saying that our true effect sizes can be splitted to what we have observed plus some error. That is what the equation is basically telling us. And then we can come to say the error. Normally it's difficult to estimate this error, the true error. For example, the whole of Nigeria. What is the true error that I have made? If probably we have included the whole of Nigerian population, I can be sure that this error of 2% is true for the whole population. However, I only sample 3 people, or probably I sample like 200 people. It's still like a subset of Nigerian population. So I still need to be able to tell what this error is. I still want to be able to generalize it or make an inference of these things. And how do we do that? Maybe people from statistics background or biostatistics, or people who have been doing this form of studies, may have come across expectation. Normally you see expectation of some values and stuff like that. Yes, we can calculate the expectation of this particular error, and then we can use that. So as an example, let me use the mean of, let's say, prevalence of maybe tramadol, or prevalence of certain, let me use prevalence of malaria. Let me use this for example, and then calculate the mean prevalence of, let's say, Nigeria. What is the error? How is it going to be different if I was going to look like the whole Nigerian population? How is this going to be different? I can decide to say, let me pick this mean, say 200 people, calculate the mean prevalence. Then I can use like form of like an iterative approaches like Markov chains or some form of resampling techniques. Then every time I resample with replacement, I calculate the mean. Every time I resample, I calculate the mean. Every time I resample from the same population, but you resample randomly and estimate the mean. So you estimate this for 1,000 times. Now do your, what do you call it, your histogram, and then you can see the distribution like I have shown here. Then you realize that this is the mean, but the means are distributed anytime I pick and randomly estimate. And then we can calculate how different each of the individual means are from the overall mean again. And that can give us like an estimate of the error that we'll be making. Of course, this is very difficult, something to conceptualize practically, but it does make sense in later on. And this is like a meta-analysis webinar, it's not statistics. So if you want to know more about estimating or understanding these forms of estimation techniques, including maximum likelihoods and stuff like that, maybe later on we can get onto books or get some articles that are introducing these things. Then we can go on. Now that we know that effect sizes are comparable, they are computationally feasible, now we can say that we want to pull them together. So it's 70 studies. Each of them is reporting their effect sizes. How do we now get the overall effect sizes from these 70 studies? That is now where we are going to right now. We can aggregate them together. So somebody on a raw note, somebody would have said, okay, let me just pick all these effect sizes together, then find an average of it. That should give me the effect sizes for the whole of Africa. Is that true? Maybe, but that is not correct. So that is why we need to get a very reliable approach in doing this. Now, we are thinking of pooling these effect sizes. How are we pooling? We are aggregating them just together, like what I just explained. All right. Hello, please. If you have questions, we can reserve it for at the end of this webinar. Thank you. Then we have the fixed effect. These are two models in a way we can pool them. We can pool proportions, Pearson's correlation, points, the serial correlation, mean differences, and then stuff like that. But now, we have two main approaches of combining these things. If we, oh my God. Dean, can you handle Desire? Who that, I don't know who is Desire. Can you check on him and then probably he will not be interrupting. So thank you. Then we have like two approaches, fixed effect and then a random effect. The fixed effect assumes that all these studies are conducted from a homogeneous population. So we are saying that if we were to estimate the impact of COVID-19 on mental health, all the individual, every single studies of the overall 70 studies that we found were all conducted among, for example, a homogeneous population. Is this true? Maybe if I'm doing randomized control trials, of course, I may have control for the set of population that I wanted. Maybe I want only pregnant women who may be in their third trimester or who may be having some form of characteristics and stuff like that. Yes, so I'm going to make sure that I am handling all confounders and then my population are homogeneous. That may make sense for fixed effect. Then once we have that, then we can weigh our studies, so then we can pull them together and then we can get our weighted mean, and that can be our pooled evidence of our meta-analytics process. So let me move on to this particular assumption. All right, I'll come down to these particular approaches later. So as an example, if you are seeing this particular plot, you would see that the first fixed effect model, you have study 1 with the round box with the round dot, study 2 with the round box, study 3 with the round dot. We are saying that technically these studies, since they are all conducted from a similar population pool, then they shouldn't deviate from each other. And then they should be the same, close to the mean. Because if really all the individual studies are reporting from the same population, then there isn't any way, there isn't any assumption to kind of make that the effect sizes are going to differ. This is what the fixed effect assumes. And so even if we end up getting that these studies are different from the pool prevalence or the effect that they calculated, it may be because they actually sample different sizes. Some of them may have sampled 200, others may have sampled 300, 500, 1,000, 2,000 and stuff like that. That may have been the reasons why the conclusion they arrive may have differed, but not because the population that they actually considered differ. That is the assumption of fixed effect model. Is it true? Not really. It's not really something that is reliable to think of, because in the real world, we are dealing with people coming from different demographic groups, age, gender, different universities, different way of thinking about things, different cultures. In fact, even biologically, different way we are designed between men and women. And so when you consider the fixed effect, that may be kind of hardcore assumption to make, and it may be very difficult to defend these kind of assumptions when you are reporting your studies. Of course, in some of my papers, I use the two of them and then I can compare. Of course, I know I'm reporting for reporting's sake, but really it's not, reliable to begin with. So Now, using an assumption of the fixed effect, we can say that the pool or the weighted mean, which is the whatever our meta-analysis is going to arrive at, which is our weighted mean, should be equal to some weight Wi times whatever effect is, let's say the R squared, then divide by the sum of all the weight. How do we calculate the weight? Pick the individual study. You know every single study may report standard deviations or variance. Pick one divided by the variance, and that can give us the weight for that study. Then put it down. For study 2, pick the weight, pick the variance, 1 divided by the variance, then write it down. Do all these things for all the individual studies. Now, when you want to pull the effect size or the pool mean or the meta-analysis, fixed effect that or this thing we want to calculate, pick study 1, the weight times the effect size, plus study 2 weight times its effect sizes, plus study 3, do that for all the 70 studies. Now, sum all of them together, divide by the sum of all the weights. Then we can get our weighted mean. This is kind of simple to do. You can do this even manually. It isn't difficult at all. But then there are softwares available for doing all these things. So thankfully, you don't have to worry about doing all these calculations. Yes, and we can actually calculate using if you have done this manually, you are curious enough like me, and you want to be able to practically understand it yourself. Calculate your variances. Then when you are done, you can probably calculate your standard errors from there, square root of the variance, and then you can always calculate your confidence intervals. Most of the times you will see studies, the effect of COVID-19 on mental health is 0.63 with 95 confidence intervals, 0.48 to 0.78. How did it come by that? Yeah, this is something simple. Just get your standard errors, then multiply. If you assume your data is coming from a normal distribution, of course, you can always pick this. The mean, the pool mean minus 1.96 and a standard error, then that can give us our lower limit. Then you can add to this particular equation, then you can also calculate your upper limit, lower limit, and then that becomes 95% confidence intervals. This is pretty simple to do, and it isn't difficult at all to do. But then again, there's a software to do that for you free of charge. So you don't also need to worry about this unless you are curious. All right. Then we come to the random effect. That is our best friend today, because that is the most reliable of all. We can't really assume studies are the same. It doesn't make any justifiable sense. So the random effect, if you see the particular diagram in my right top right hand, you will see study 1 dot, study 2 dot, study 3 dot are all different. They are not on the exact same line like we saw before, but they differ from the mean by some margin. So at the end of the day, we are only estimating distribution of our individual study effect sizes. Then we have to be able to acknowledge that, yes, we are saying even the sampling strategy or the sample size alone is explaining why there are differences, but that isn't the only reasons why we are different. There may also be some genuine reasons why there is that variances. May include that your studies participants may come from different cultural backgrounds, different demographic backgrounds, different biological makeups, so many reasons why our study will not be the same. And then we have to factor in this external source of error, add it to the sampling size error, then we can be able to arrive at a random effect. So technically, that is it all. We are saying our fixed effect, our true fixed effect is coming from some mean, but then this mean also have some errors associated with them. One is the sampling error or standard error, plus some true error about the differences existing between studies, which we don't know. But we later on, as you get better and better in meta-analysis, you may come to appreciate this quantitative, explanation quite clearly. And then we can move on. These are a little bit more of maths, and I'm not going to explain all these maths. I will make the slides available. You can go through all this, be able to figure all this out. Fine. And then we have the, All these things we are doing that, all of them relies on something we call tau squared. If you may have been doing a lot of variances and stuff like that in your studies, you may have been coming across tau squared, tau squared, tau squared in most of the time. In context of meta-analysis, that is a measure of the true variances. That is a measure of the true variance. So if we knew about the entire population of Nigeria, the variation that we see there is the true variance. And that is what the tau squared is helping us to approximate. So it is more of like using like a form of like maybe maximum likelihood estimations or some form of estimations to do them. In meta-analysis, normally we estimate this thing with different approaches. We have the Des-Simonian-led method, which is the most commonly used one. In fact, if you download 10 meta-analysis papers, the likelihood that you see Des-Simonian-led in 8 of them is very high. And you also have the restricted maximum likelihood, which is also an improvement in the maximum likelihood estimations, but it's restricted between some lower bound and upper bound, much more different than the maximum likelihood estimation. And we also have Paul Mandel approach. We also have the empirical based approach. We also have Siddick-Jonkman. So there are a lot of them. Which one should you use? Depends on so many things. From the literature search, I realize the sample size, the number of studies you are including, and even the variances in your sample size can all determine why you should use one over the other. If you are dealing with, continuous data, that is my bit of advice that I had from the literature. If you're dealing with continuous, like the impact of COVID-19 on mental health, this may be on a continuous measurement scale, then you should begin with the restricted maximum likelihood. I have tried the Des-Simonian-led and restricted maximum likelihood. Sometimes there isn't differences in the estimate, but then we recommend more of the restricted maximum likelihood because that gives more precise estimate. And then later on, you can begin to see that the Des-Simonian-led method is also somewhat flawed somehow, and I'll explain that later. And then if you are coming from Paul Mendel, you can also use this particular estimation technique if you're dealing with binary outcomes like logistics, or ratios, risk, relative risk, and stuff like that. Paul Mendel may be a good start for you. And that one, but make sure that there isn't extreme variances in your sample size. So one study is not using only 20 people, another one is using 10 million people. If you are dealing with such scenario, then Paul Mendel isn't a good for you. Go back to the maximum likelihood, the restricted maximum likelihood. Siddick-Jonkman is also another, which I don't know much about. I've never used it, and I don't know under which scenario I'll use. Then we come to the heterogeneity measurement, which is very, very important. In your meta-analysis approaches, you would always come across people measuring effect sizes, which we have talked about for some time now. Now we have been able to calculate our mean for all the 70 studies. We realize that the impact of COVID-19 on mental health having a relative risk of 1.47, which means 70% higher for people who have COVID-19. Yes, this is like a mean. How do we? Hello, please. Oh, of course. So we come back to the heterogeneity. We should be able to explore this particular relative risk of 1.74 we saw. Is it the same for all the individual studies? Of course not, because that is what our random approach told us. The studies are coming from different populations. So the conclusion we arrive at 1.47 is likely not to be the same for all the individual studies. Can we quantify how differences these are? Yes, we can. What can we quantify the magnitude of how these differences are, how big these differences are? Of course we can. Then that leads us to the concept of heterogeneity measurement. But before I start with the crazy equations, let me make it clear that there are two different types of the heterogeneity. Those that are by design or that is coming from the baseline ones, and those that are statistical heterogeneity. So you just sample people from different populations, or perhaps the instrument you use for even measuring this, whether somebody is mental health, derail, or something like that, may in itself be different. So this is by design, the variances are going to exist. This is like a design approach. And we also have the statistical one, those that are random, like sample size. You calculated sample size and then you got it. Somebody else calculated, he got something different. So at the end of the day, all of you are coming from different sample size differences. And because of the sample size, your variance at the end of the day will vary. But it's not your fault because it's a statistical heterogeneity. So yeah, these are the two critical heterogeneity types that we can think of. Those that are by design and those that are statistical heterogeneity. Statistical heterogeneity may come from the sampling, the baseline may come by the design, the population you are considering, the instrument you are using to measure your whatever you are dealing with and all that. These are stuff like that we have to consider. Now, in a meta-analysis, almost all studies you come across will use something we call Cochrane scale. Cochrane scale as a measure of how big our heterogeneity is. What does it mean by Cochrane scale? It tells us how much of the variances is actually due to the true differences between studies. Because we realized that the fixed effect was saying that there isn't any differences at all. But if there is any difference, then it's because of the sample size, right? Now, we are saying now the Q is trying to tell us how do we segregate or how do we divide these differences so that we can tell what is the proportion of these differences that is due to only true randomness, because we are coming from two different population, different demographic backgrounds. Then we can use that. And then the Q by equations should be the sum of the weighted square differences, So we pick study I, the fixed sizes, minus whatever you calculated for the random, for our meta-analysis, like the relative risk of 1.74. We can pick the study 1, minus whatever we found about the 1.74, square them, then weight it by the study's weight, which is 1 divided by its variance, like I already mentioned first. Do that for all the individual studies, then sum them together. That becomes our Q. And that is something we are actually doing two differences together. And you see the WK represent the invariance, like 1 divided by the variance. And we know by fact, variances always relates to the sample size, like the sampling error. So if we are multiplying the differences between the two studies, the study and its overall effect, times the weight of the study, then we are basically measuring the Cochrane scale with two different error sources, random error sources, and then true variance sources as well. And that can give us the overall Q. And that is really a good start, but then there are a lot of critics about this approach. You would realize that by design, the more the study increases, looking at this equation, if you understand the equation intuitively, you would realize that the more the study increases, the more the Q increases. And that is a problem. That is really a big problem, because you just don't want to do that. You want to know a Q that is independent of the samples of the study size. That is the best approach. We want to still know how much is our Q, regardless of the study size you are using. And that isn't what Q is giving us. So most people have cautioned us against this. And I can go on to tell us why the decimonial lead may be flawed in somehow, because it relies on these approaches in calculating the tau squared. Now, we can come to the I squared to measuring. And this I squared is much more better because that one gives us percentages, taking effect into the degree of freedoms that those of you who are already in statistics, you appreciate degree of freedoms. Now we can pick the Q that we calculated earlier, minus the degree of freedom. So if you use 70 studies, then the degree of freedom becomes 69. Then you divide it by the what do you call it, the Q again, then times 100%. And then we can get our I squared. And normally that's what studies report. If you see most meta-analysis, if you study meta-analysis without seeing R squared, that would be very weird, because I squared is very popular. But it also becomes a problem because the number of studies increases, then the I squared also increases, which is a problem, because just the fact that I'm having 200 studies or 300 studies doesn't mean the variances should be that big. All right, thank you. So we have the I squared increases as the number of studies also increases. Why is it the case? Because there is that inverse variance, the inverse differences. The higher, the lower the standard errors, then the more the true variances become. Because we believe these particular true differences between studies and a sampling standard error are both combined together in one single studies. That's what we believe. But then the more this, if we assume that the bigger the sample that we calculated, then the standard error becomes slightly higher and slightly lower, sorry. Or then that means that the differences or the true variances because of population differences will become down higher. So there's that particular by design inverse relationships between the true variances and that of the standard errors. And that goes on to tell us why the I squared also is not entirely also reliable. Because if really somebody using 50 studies will get low I squared and me using 70 studies, I'll get higher I squared, then there isn't anything meaningful to rely on it in the first place. And that is it. It's a critique. And most studies are ongoing. They publish a lot of studies, tens of studies to prove why I squared is not reliable, including the Q squared. But then it doesn't mean you shouldn't use it, but you should use it with caution. You should be able to tell, our readers how we should be interpreting your results. Then we have another weaknesses of it. You realize that by design, looking at the equation of I squared, if you have the degree of freedoms higher than the Q squared we calculate, then we are always going to get I squared to be negative, which isn't something really, which we don't want to have like negative I squared. So whenever you have like degree of freedoms like 70 and I squared being, let's say 60, then you're going to have negative 10 divided by 60. It's going to give you like negative 0.6 or something like that. But that is a problem. And so anytime we have like such negatives, then we replace the negative with 0, like I squared of 0. There isn't differences at all, which is a big problem. They may be, but then they are negative. And so we have to be very careful about that. Then we move on to the H squared. And the H squared is able to handle this and pretty much better because you realize that the H squared can always get smaller and smaller and smaller as our degree of freedom becomes bigger, but it never becomes negative. The lowest it can be is 0, but never negative. And that is a very good thing. But it still relies on the same Q squared. So the same weaknesses that I pointed out earlier still inherently is in H squared. That is also a big problem. Now, which one should we use? Depends. Most of all of these three I have mentioned have their own weaknesses attached to them. But then you can report, I normally report all of them because the statistics software gives you all of them. I report all of them. And then you can decide which one you are going with. There's also an example of the tau squared. Some of them believe, or statisticians prove that the tau squared itself can be a measure of the variances. Yeah, but also there's a big problem. How much is the variances? How much is it? We don't know. By percentage-wise, we can't tell. So there's also a big problem. And then there are also people who believe that we should use the prediction intervals in addition to the confidence intervals to tell us that, okay, if our confidence intervals ranges from 1.2 to 1.74, then what is our prediction intervals? When we consider all the broad range of possibilities across the world, where would our prediction of these particular scenario fall? Maybe it may include 0, may include negative values. Then we can know that, oh, our conclusion isn't really, really reliable. And so we should be very careful about that. So some of them believe that we should use the prediction intervals in addition to all the Q, the I, and the H, so that it can give our readers comprehensive, what do you call it? Assessment criteria. So you can know that we have access to our heterogeneity and stuff like that. But then by design there are some studies that are also going to have some influence in the overall mean that we arrived. So we arrived that, okay, the impact of COVID-19 on mental health has a relative risk of 74. But then if you include 70 studies, is there 1 or 2 studies that is having very strong influence on our conclusion or not? Some of them may be. If there are, then that's a problem. And you need to be able to report them or exclude these studies and tell the researchers or everybody that, of course, these are the only 2 studies that is determining the effectiveness. And that alone itself is also a significant research findings. So how do we know which studies are much more influential and which of them are also outliers? Outliers by nature may be random noise, maybe a noise that we have to take very care of, like for plotting your graph or plotting your histogram chart, and you just realize there are extreme values that are far away to the left or right of it. That can sometimes skew your data. So from statistics standpoint, outliers are always something difficult to deal with. In meta-analysis too, they exist. Some studies may report outlier values that do not overlap with our overall mean of 1.74. And so we should be able to exclude them or do some sensitivity analysis, report 2 different values, 1.75, including that studies. So let's say we included study 1. That study 1 inclusive give us relative risk of 1.74. Once we exclude this study, then our relative risk decreases to like 1.54. Then that study alone is taking care of 0.24 of it. Then you can report these 2 things that, okay, in the study, just report them in the study. Doesn't mean you should exclude them. You can still report them. The findings inclusive of that study and the findings excluding that study, you can report both of them. It can be useful for multiple readers out there. Then the fact that we have an outlier doesn't mean it's going to change our relationship. Maybe it decreases the effect small. For example, like the one I just mentioned, it decreases from 1.74 to 1.54. But does it change the relationship? Maybe not. But the influential studies can. It can change the effect altogether, that the relationship between 2 variables may become negative. Once we exclude that study, then the effect becomes negative. Once we include them back, then the effect becomes positive. They also exist. And we have to be able to handle these things very well so that researchers may know and find very critical about it. And thankfully, meta-analysis in softwares are able to handle some of these things and report to us. I like using R for these things because the code is simple and it can generate you all these things with a simple line of code. And you can see here, we have to my right chart, you see some that looks like a time series chart with red flags in some of the studies. These are all the studies that have been flagged as as something influential or having an outlier effect. We can include these studies and then report what is or maybe report different values, inclusive and exclusive, but it's very good to identify them. And we also have to other aspect of it, we have like a particular chart with big boxes with some level of, what do you call it? Green circles, each with a study sub box. And we can also do this, something we call influential studies. And it can tell us that one of the study is separated far away from the rest of them. And that can change the effect altogether for that for your meta-analysis. Identify these studies and probably exclude them or include them with caution. So that your people can be very wary of these particular findings. Then we have if you are in R, then you can easily use the influential analytics or influential analysis in DMeta. It's like a package. DMeta is a package in R that you can easily call, install for me DMeta, and then call the library, and it will be for you. So you can basically, with a simple line of code, you can easily get them. And then you can even, export this particular graph that I'm showing to you here and include it in your studies. So those who don't even know statistics by detail can actually look at this chart and tell you, okay, study 1 was very influential. That's why I excluded them or included them with caution. Yeah. Okay. Then what are some of the notable softwares? We have comprehensive meta-analysis, actually not for free. Yeah, so you should be able to, if you want to license for it, you should pay for it. R with meta-analysis for free of charge, but that also comes with it. You also have to know how to code. So yeah, if you also know how to code, you can get somebody who can code for you with critical guidance on the concept. Raveman, Review Manager, is also good, so developed by Cochrane. It's also free for that. Stata, not for free, because you also have to go to get the license for it. We have the JASP, also free. Meta Excel, I don't know if it is free or not. WinBacks or OpenBacks, I'm not really sure if it is free or not, but it is very useful for doing Bayesian meta-analysis. I've not mentioned them here because that is an advanced form of it, or different form of meta-analysis that should be handled. Probably in our next webinar series, I can introduce the whole of the hierarchical models or Bayesian models with WinBacks and OpenBacks. MetaMix is also for a very good use for mixed meta-analysis, where a lot of your studies may be including random effects, fixed effects, and all those things jammed up together. If you're dealing with such particular scenarios, then mixed meta may be a very good thing for you to do that. And then there are some references here that can be useful for you. These are some of the milestone, references that you can use on to get to know more about meta-analysis and stuff like that. I will share this slide with Dean and then Fortune. They can always share with you guys, so you can copy and paste in Google search, and then you can get them and then read. All right. If I could say that's exactly 11:34 in my time, Eastern time. And this is the end of the brief introduction we have had. I should caution you, you may read more extensively and come across a lot of techniques that are actually not mentioned here. You cannot become an expert just by attending one webinar series. You need series of them, and you need extensive learning. And probably we can organize other different series to really treat these things so that you can become more familiar with it. But then you can read more of these articles as well, and then to get to know yourself the better. All right. Thank you for your attention, and thank you for being attentive and not disrupting much. And I can give it back to Dean to give us this particular kind of questions. Those who have questions, they can ask.
Thank you very much, Moses, for this wonderful presentation and introduction on meta-analysis. Please, we will now open the floor for 3 questions. If Moses does not mind, we are going to take 3 questions, and other questions can be sent to us via our email.
Yes.
I'm going to drop the email on the chat box so that people can have it and send their questions. And I just want to remind us that there is a post-assessment form being dropped at the chat box, as well as our other social media handles. Thank you. Over to you, Moses. 3 questions, please.
I can see Ifo Ikena raised his hand. Can you please go ahead?
Okay. Hello, everybody. Good afternoon. Thank you very much, Moses, for this wonderful, wonderful presentation. In fact, I would like to reach out to you later. If possible, they can send in your email address so that we can always reach out to you later. Thank you. Okay. So my question is, you said that when we are doing a meta-analysis, you have the different, what they call them, there's something you call them, like you have the Pearson, you have the risk and odd ratios. So yes. When you are saying you add up the effect size, I think it's effect size, yes. So when you say you add up the effect size, are you going to just add up, the effect size using Pearson only? Or would you add up doing Pearson, risk and odd ratios, and the other different, what they call them? I don't know what to even call themselves. Yeah.
Yes, I understand. I understand where your question is coming from. All right.
So that's one question, please. Let me ask another one.
All right.
Sorry, I wrote them down. So that's okay. Okay, then I don't know if you told us how to get the error, how to get the error when we are calculating the total effect size. I tried looking for the what they call it, the formula, and I did not see it. I think that's all. Thank you very much.
All right. So if you are doing with, let's say, the impact of, let's say, COVID-19 on mental health, actually, I'm mentioning a lot of mental health because currently I'm working on mental health impact, environment, green space impact of mental health. So if you are dealing with such scenarios, then the best you can do is to make sure that or maybe include only studies that are reporting in, let's say, odd ratios. But then there's always like a convention between odd ratios and then risk ratio. They are correlated somehow. And in fact, if the prevalence that you are trying to estimate is always less than 10%, then they estimate the same thing. So there isn't any problem to worry about. But then make sure you're not pulling correlation with relative risk. They are not the same. The relationship between X and Y are just only coming from covariance metrics. And technically, they are not measuring the same thing as relative risk. So if you are coming from medicine field, make sure you stick to one single metrics of measurement like relative risk, and then use that to pull your estimate. Don't combine correlation tests like Pearson correlation plus relative risk. It doesn't work that way. It's like trying to say I'm combining orange plus juice plus pineapple, and I'm going to get some fruit. No, it doesn't work that way. Then to your question about measuring the true variances, that is like tau squared. If you want to measure the tau squared, of course, you don't have to do them manually. There are softwares that are available to you. They do them automatically. You can check for the Simonian-led model. You can check for Mandel.
Yeah,
Mandel
you named them.
Yes, you can check for relative maximum likelihood or the maximum likelihood. All these are processes for estimating the true variances. And then I have given you a rule of thumb as in which one you should choose under which scenario. And I'm sure
Thank you.
Listen to
Please,
them.
the last question. Sorry, before I saw that you mentioned Stata as one of the one of the tools we can use for meta-analysis. So I know that Stata and GraphPath Prism somehow they are related. Can we use GraphPath Prism and SPSS for meta-analysis?
Yes. SPSS can also be used, but there are specific functions that I know that functions like R, for example, have very, very, very extensive tools and packages for dealing with some complicated scenarios that SPSS may not have. And I know for sure Stata may have some advanced methods that SPSS might not have. So depending on how complex your meta-analysis is, you should be able to stick to those that I've mentioned here.
What of GraphPath Prism? You didn't talk about it.
Yeah, it's also I've never seen it reported anywhere that they used it before. I don't know if they use it. Yeah, but you should check that and see. Yeah.
Thank you.
All right. Is that the end?
Yes, I have some questions in the chat box, but if you want me to raise it now, I could repeat it.
You can raise it.
Yes, that's the
Thank you
second
for your
question,
presentation.
please.
Yeah, thank you for your
Excuse me, that's the-
presentation.
Yeah, I want to ask a question.
The one who previously talked
Yes.
about the question?
Yes,
this
me here. I'm here. Thank you
this
so much.
Oscar
Yes,
Onanai.
I was going to ask about the representativeness of the sample size. How do we calculate that? At the same time, the second question, you also talked about inclusion of thesis and then preprints, which have not been reviewed. So I was wondering, don't you think that will lower the confidence of the results to the research audience?
Yeah, so the issue is handling your effect of random sample size. There is an issue if you are dealing with primary studies, then you have a control over that. There are a lot of methods for calculating sample sizing because you go to the field to collect or interview your people, or do your randomized control trials. There are calculations, and you can assume the error that you want to make should be 5%, 95% or confidence intervals of 95. Then you can use that one to calculate, credible confidence for your sample size. But then if you're doing meta-analysis, you don't have that control. But then you have one control. You can decide to say, okay, since I'm going to pull something, I don't want all sample sizes that are reported for studies below, let's say 30. So if I see a study that uses a sample size below 30, I'm not considering that at all. Why? Because that one has a deep philosophical answer to it. If you're dealing with sample sizes above 30, then you can always use z-scores and then calculate some 95 confidence intervals with normal distribution assumption. But if you're dealing with sample size below 30, then you're using t-distribution, which is somewhat an approximate to normal distribution and some form of z-test and stuff like that. But no. So you should be able to do that. I normally use like a cutoff of like 30. Yeah, but then the higher the better. Is that your question answered?
Yeah, it is. It is, except for the other one, the inclusion of the other non-reviewed papers like thesis.
Yes. So yes. So there's always
I
example.
justify that.
Yeah. So the issue with it is that there are theses are also reviewed by experts as well, because nobody do like dissertation and you just write anything at all you want and then graduate and go away. You still have to get committees who also review it. That's some of the arguments made by some literature. And their issue is we also have the way of doing sensitivity analysis. I mentioned about influential studies. I mentioned about outlier studies. There are ways of calculating it. For example, leave out one analysis. You can always use this iteratively to calculate and exclude this thesis and see if your effect size changes or not. If it changes, then explore the quality of it. If it doesn't, and of course, there's also a way of also quality assessment tools, risk of bias tools. All these things can also be subjected to the dissertation as well to see how best they also can be included. Okay. Is your question answered?
Very well. Thank you so much. Michael Awole from OAU. Thank you.
All right. Thank you.
Yeah. Good afternoon.
All right. Good afternoon.
Yeah, Senior, my question has to do with, there was a paper I was working on and I wanted to run, I used Jamovi to run my meta-analysis.
Okay.
However, I was trying to use the Pearson correlation, but one of the papers do not have the Pearson correlation. However, the 9 has. So what am I going to do in that circumstances?
Yes. If you, what do you call it? Which method was, what that particular paper, what metric did you measure in?
You are taking me to the highest level. Or?
I'm asking, like that particular paper, what is it measured in relative risk or something like that? Why is it, which method did you use?
Yeah, it was measured in relative risk.
Okay, so I know for if you are using comprehensive meta-analysis as a software, they have a way of converting between one to the other. But I would suggest you search and see if there is a way, the formula for converting, what do you call it, relative risk to yeah, to correlation, Pearson correlation. If there isn't any, simply exclude that studies.
Okay, thank you very much.
You're welcome. All right, is that the end of the questions? If you have
yes, I have one, please.
All right, you go ahead. This is the last question we can take.
Okay, thank you. Is it a good idea to do a meta-analysis of qualitative studies reporting prevalence as the outcome variable?
Yes, I am. If you have, let's say, prevalence that is measured, let's say the percentage of people that are sick of certain diseases.
Yeah.
Of course, if they have reported that, that also depends on the sample size, because I know for most qualitative studies, they don't always use very great sample size, like 30 people, 20 people. If you're dealing with such scenarios, then it's not really advisable. But if really they were doing the qualitative study, but they reported the prevalence, and then the sample size is good enough, like 1,500 and above, then I think it can be included. Yeah.
Okay, thank you.
You're welcome. All right. Thank you, everyone, for attending this webinar series. Our next webinar series will focus on assessing publication biases and then how to deal with them. And then our last one will focus on practical application of it. And then I'm sure, pretty much confident that this introduction will at least give you some confidence when the 2 webinar series are enrolled. And then with as time goes on, we might repeat the same process for those who didn't get to understand this first webinar series better, especially the introduction is very, very critical. And then thank you for all, and then do enjoy your day.
Thank you, Moses.
Yeah.
Thank you very much.